Log on, tune in, find out. Another good idea from Cambridge.
Again, now it's a very, very privilege for me particularly to introduce Professor Bernard Carr. Bernard and I were contemporaries reading the mathematical tripos at Trinity some time ago now, and I particularly remember the wonderful garden parties at Trinity Fellows Garden that Bernard used to put on after all the exams were over. And it's great to have renewed contact after these years in this sort of context of science and religion and multiverses and so on. Bernard has had a distinguished career. He went on to become a fellow of Trinity, and he did his PhD with Stephen Hawking, and he had a senior fellowship at the Institute of Astronomy, and then moved on to Queen Mary University of London, which is where he is now as a professor. He has a strong interest in this relationship between science and religion, in the area of consciousness, and of course particularly the area of multiverses. And there's this wonderful book, very highly balanced book, as George was saying, Universal Multiverse, that we have on our bookstores. It's a great pleasure to have you with us, Bernard.
Thank you very much, Rob. Well, it's a great honour to talk about Lemaître. I'm not a great expert on Lemaître, and I've been fascinated to learn about all his contributions. I mean, I knew about them in the general sense, but to learn about the specifics. And I've given us my title, something which is, of course, a reference to Lemaître's great contribution to cosmology. But actually, most of the things I would have said in that context have already been said, so I'm going to take the talk well beyond that particular topic, as you'll see. Plan of my talk, first of all, I am going to say a little bit about Lemaître's contribution, but that will be very brief because we've already heard so much about it, especially on the first day. And then I'm going to talk about, I'm going to take sort of each of the two key contributions of Lemaître and sort of expand them in a direction which is of interest to me. I'm going to argue that his concept of the primeval atom is the first step in really what has been the great triumph of physics in forging the link between the micro and the macro worlds. So therefore considered in the context of physics. And then I'm going to be saying how his work on the cosmological constant, the future of the universe, is going to relate to the whole question of fine-tuning and the anthropic principle. So basically I'm going to use Lemaître's two great contributions to lead me into the two topics which are of great interest to me. I'm then going to get on to the topic again of the multiverse. Now obviously Don and George have already spoken about this, given somewhat different views. I've myself had dialogue with George about this in the past. I just want to say a bit about this, but not too much. But in particular I want to stress something which I think is quite important because it arose out of Paul's talk this morning, and that's to do with the changing nature of science. To me, to be honest, the question is not whether multiverses exist. The question is whether multiverses are science, and that's precisely what the question George raised. And I tend to take a different view from George. I tend to think it is science, but you have to extend what you mean by science. But of course, it's all open for debate. And then if I have time, I will even get onto these issues, the more metaphysical issues, which I couldn't talk about in front of physicists, but I can't anyhow. I'm going to talk about the links of these ideas with consciousness and even God. So let me then just start off very briefly just by summarizing Lemaître's contribution. We all know as we've heard it, so I'm just going to summarize it very quickly. We know about of course, the Einstein static model, the Sitter model in 1917, and the Friedman model in 1922. And then we know, of course, Lemaître's great paper came out in 1927, where he got Hubble's law and even Hubble's constant. It preceded Hubble's paper by 2 years. Then, of course, we had the Eddington-Lemaître model, which you heard about from John this morning, 1930. The translation of Lemaître's paper in Monthly Notices in 1931. With us, we heard some missing paragraphs. And then in 1931, there was his famous proposal of the primeval atom, and the Big Bang came to be known at the British Association meeting. I think that meeting was on the topic of cosmology and spirituality. Is that correct? That was quite interesting, relates to this meeting, I guess. And then there was this paper in Nature that followed that. And then there was his famous work which on the Tolman-Bondi, so the Lemaitre Tolman-Bondi solution, which, I've missed out the name Bondi, sorry there. This actually was the topic Bill Sturgeon would have talked about if he had been here. So I'm sorry about that. And then, of course, we heard from John this morning about how he not only studied the cosmological model from lambda, but he also had the prescience to understand that lambda we thought of as a vacuum density and even had fluctuations. And then his book came out in 1946. So that's a very brief history of all his contributions. I want to show this picture again. David Bloch showed this, showing how Lemaître himself predicted the Hubble constant 2 years before Hubble. And remember, this picture wasn't plotted by Lemaître, but this is the data which was used to get the value of the Hubble constant. So in some sense, he would have gone through that calculation, though I don't think by actually drawing that diagram. And there was some controversy yesterday about, really, from this historian science point of view, well, does this really matter very much? To be honest, in cosmology, almost everything is named after somebody different from the person who discovered it. But to me, actually, what's interesting about this, I mean, I get the impression some people are angry that Lemaître didn't get the credit he deserved, but I have the impression that Lemaître himself didn't seem to care very much, which seems to say something interesting about Lemaître. He's clearly has a modest person. But anyway, this is the key point. This, of course, is the famous diagram showing the Lemaître model, which starts off with the Big Bang and then goes through the coasting phase when galaxies form, it accelerates, and then, in principle, it may expand forever, according to like the de Sitter model. And this single slide, which I borrowed from Michael Heller, really encapsulates the huge prescience of Lemaître, in that he not only was the first person to understand the beginning of the universe, the Big Bang, he was also the first person to anticipate and think about the future of the universe, what we now think of as the future of the universe, if the universe is going to, if we are indeed dominated by dark energy, as most people assume. I would like to stress, however, that we don't really know what's going to happen in 10 or 100 years or whatever it is. It is still possible the universe may collapse. If the curvature constant is positive, we could still collapse. It would be in a long time. And we could even have more dramatic ends if the nature of that dark energy is what's called phantom. We could end up with a big rip, which is even worse. So we don't really know what's going to happen. But the point is that this concept that the universe is going to expand exponentially for a long, long time goes back to Lemaître. And that's really a stupendous achievement. I call this prescience, Lemaître's prescience in the title, and I was being a little bit ambiguous with the word prescience. Prescience, of course, means anticipation, but I also read that as pre-science. Because actually, when these ideas were being proposed by Lemaître, it wasn't clear whether it was respectable science at the time. Whether people didn't believe the Big Bang, and they certainly wouldn't believe speculations about 10 to 100 years. And this really relates to the question which Paul raised this morning about the border between cosmology and metacosmology, between science and meta-science, if you like. And I'll come back to that. Well, that's all I want to say about Lemaître. But what I'm going to do, as I said, I'm going to take these two issues about the beginning of the universe and the end of the universe and use those to trigger two things. And let me start off about this link between microphysics and macrophysics. Now, we had a wonderful talk this morning by Paul, talking about the great observation of the stars. I can summarize all that because he did it so well in just a few minutes. So there's the Hubble field. That's our picture of the universe. We heard how one of the great discoveries was the realization that the universe is accelerating. and this is the cover of Science. This was the evidence from the acceleration coming from, I think we heard about from Paul, giving cosmic convergence to the standard model. And just to remind you that the evidence for that comes from essentially an extended version of the Hubble diagram, the Lemaître diagram, and it comes from making observations of supernova. There is a supernova. Supernova will come back into my story later, so there's a nice picture of a supernova. Those are the supernova. Those are the things which have told us that the universe is accelerating in direct observations. The other thing I should remind you is that actually there's not only dark energy, but there's also dark matter. And as far as we know, they're not connected. And this is a dyed little picture borrowed from Joel Premack. And this just shows that you've got this sort of cosmic density pyramid. The ordinary matter at the top, first of all, the visible matter is something like 0.01%. The ordinary baryonic matter is 0.5%. Then the visible ordinary atoms are something like 4%. This is the total density. But then we know there's cold dark matter, which is about 25%. And then there's the dark energy, which is the rest of it, which is about 70%. So we got more precise figures in Paul's talk this morning. And so that's a crucial thing to bear in mind. As I think you said it very nicely, nearly everything in the universe we don't know anything about. Now, we also learned, of course, about the microwave background. This is the famous W-map picture, and the huge information that gives. And it's the evidence for this, what's called here the double dark. I've also borrowed Joel Premack's slide here, the double dark theory, the dark matter and the dark energy. It comes from a variety of things that we've heard about. It comes from observations of structure in the universe. It's what's called a power spectrum, going all the way from the smallest things like intergalactic clouds through galaxies and clusters of galaxies to the microwave background. Sorry, look, you can't copy that all down, but I'll show it to you later. And this is the famous bumps in the microwave background spectrum, the anisotropy on different angular scales. And as was explained this morning, it's the size and the position of that bump on its angular scale which gives you information about how much dark matter and how much dark energy there is. And so, I mean, it's just amazing, really, when people, Paul mentioned it this morning, but when people first looked at that microwave sky, it was just unbelievable because, you know, as a cosmologist, for many years, you work on all these theories, and I guess part of you think, well, maybe it's just a mathematical game, maybe it's not real. And then when you look out at the sky, and you find what you've been working on for all these years is actually real. It's an amazing feeling. So anyway, that's the picture. Now, of course, nearly all the slides have been shown, but I'm glad this slide hasn't been shown, so I can show that. This is just a summary of the history of the universe. Starting with the Big Bang, and here's your inflationary, so the size of this is the cosmic scale factor. So you start with your inflationary phase, and then eventually that's the microwave background there, which you're looking back at about 400,000 years. Stars, actually galaxies form, and stars and planets form. And now we're accelerating due to this dark energy, and now there's the W-map satellite, which is looking back at the microwave background radiation. So that's a nice summary of the history of the universe going back 13.7 billion years. The only thing is now, of course, we must replace the W-map satellite with the Planck satellite. So the W-map obligingly died. So that's the sort of summary. And so, if you like, as a way of understanding, remember that essentially in cosmology, when you look to larger distances, you're also looking back in time. And so you can think of us as sitting in the middle, looking back in time to shells at ever and ever greater distance. And so this microwave background is essentially, you're looking back to when the universe was about 1,000 of its present size, 400,000 years after it began. And that's almost the furthest you can go. If you look back all the way to the Big Bang itself, you'd just be looking back a little bit further. So you can think of that like a sphere on the sky. Those are the cosmic spheres. But then the question is, of course, well, this edge is just the distance light can travel. As Martin said in his talk on Thursday evening, it's like a horizon if you were looking from the top of a mast of a boat. And of course the universe itself doesn't end there. So the question is, what does lie beyond that horizon? Well, of course, we're not in the domain of observational astronomy by definition, but people can speculate, and you've heard a bit about the multiverse idea. But what is clear is that our visible universe is just a small part of something bigger. So I would say that all there, well, I'd like to spend my life on it. However, then when you get these speculations about what exists beyond that, of course you're into the domain of speculation, imagination is described. This is a particular multiverse scenario in which you assume that this little bubble is just one of many, many bubbles, and that the multiverse, as it's called, is a huge extended structure. Of course we don't know, but the whole point is to stress that our universe is just a minuscule part of some larger physical reality. What that larger physical reality is, or even whether you should call it physics, is of course speculation. Now, so that's talking about what's been achieved by physics or cosmology. Let me now say a little bit about what's achieved by particle physics, because of course I'm going to talk about the link between macrophysics and microphysics. And you all know this, but it's that you can think in some sense of the history of physics, or particle physics, as the attempt to unify all the forces of nature. That's one of the key features of physics, is getting this unified description of the world. So of course first electricity and magnetism were unified, and electromagnetism. And then by Maxwell and Faraday and people, and then that was unified with the weak force, the weak theory in the 1970s. And then that's been experimentally confirmed, and then from a theoretical point of view, we also know that we can unify the strong force with electroweak as part of the grand unification force. And then, of course, the ultimate aim is to unify that with gravity. So that's the final dream, and of course we know that the currently popular approach to that is M-theory, which is an amalgamation of all the different versions of superstring theory. And so really, the great, of course we don't know this is true, but the great triumph of physics is to show that, in some sense, all the different forces of nature seem to be different manifestations of a single interaction. But there's a price to be paid for that understanding. That is the fact that M-theory, for example, is rather complicated. And it involves rather strange concepts which themselves might be regarded as a little bit beyond normal physics. In particular, it involves the concept of extra dimensions. And the number of extra dimensions varies. I mean, we know we have 4 dimensions, we're quite familiar with that. Kaluza-Klein said, well, actually, there's an extra spatial dimension, so there's 5 dimensions. The original superstring theories had 10 dimensions. M-theory has 11 dimensions. So we've got all the extra dimensions, but the extra dimensions are all wrapped up in some you don't notice them because they're compactified. And the Calabi-Yau is the sort of space which is described as compact space. And of course, and I have to say, I use this on the cover of my book. It's such a beautiful picture. And we've also heard this morning from Don, I think, about the string landscape scenario, because one of the points about M-theory is that there is not a unique vacuum state. The original hope would be that there was a unique vacuum state, but now we know, as Don described, that actually there seem to be maybe 10 to the 500 states, each of which corresponds to a different value of the cosmological constant, essentially. And so that's that picture. And so here is, if you like, just a summary of this rather strange picture that how, as our understanding of physics has progressed, the dimensionality of the world has increased. So Newton had a 3-dimensional world, Einstein 4-dimensional, Kaluza-Klein 5Ds, superstrings 10D, M-theory 11Ds. And in a particular model, which is the brane model, we think of our universe, our 4-dimensional universe, as just being a brane of a sort of high-dimensional bubble. Of Of course, this is all speculation, but it's the sort of idea that we'll work on. Okay, so that's my introduction to physics. Now, this is summarized in this beautiful diagram, which I'm sure many of you have seen. It's called the cosmic Ouroboros. It's the snake which is swallowing its own tail. And what you do in this diagram, you put around the edge, it's a sort of ruler, and you put all the different scales of structure which exist in the world. So we start with men and women at the bottom, and then we go up to mountains and suns and solar systems and galaxies. And we end up at the scale of the physical universe. And on the smaller scale, as we go to the left, we have things like amoebas and DNA and atoms and nuclei and dark matter particles. And we end up at the Planck scale, which I've not even written here, 10 to the minus 30 centimeters roughly, minus 33 centimeters. And so that's this is the, to me, beautiful image which captures everything we've discovered about the universe. And at the highest end, of course, we've got the multiverse, because what happens when you get to the head, the tail, the very big merges with the very small, and you've got the multiverse on the right side, and you've got M theory on the left side. So that's, for me, a very beautiful picture. And, of course, something really weird happens at this top, and it seems to be something to do with higher dimensions, both from an M theory point of view and from the point of view of the multiverse. And just to, of course, the key point about this, why does the very large merge with the very small? Well, the reason for that, of course, is that when you look back in time, when you look to larger and larger distances, you're looking to earlier and earlier times when the universe was smaller and smaller. So that is why, ironically, when you look to the larger distances, you're looking to the smaller scales. And this is illustrated very nicely by George's picture, which I'll show again, which shows how the light, in a space-time diagram, it shows how the light curves behave. So when you look to very, very, very large distances, what you think, looking back further and further in time, you're actually going to very, very small distances. And in some sense, the shape of that space-time diagram, in some sense, is explaining why the very top and the very bottom merge. Now I want to tell you a story. I want to go through that diagram in a series of steps to give you the history of physics. Because that is the history of this link, which, of the link between microphysics and macrophysics, which, in a way, Lemaitre started by when he had the concept of the triangular atom. And so I'll go through this quite quickly, but it's just a way of summarizing, in some sense, all the progress in physics and showing how it all connects. So I just want you to think of this as a story. So there's our, I'm going to sort of tell a story about that cosmic Ouroboros. So here's the man and the woman. And now I'm going to be essentially describing the progress of science as we've looked at ever larger and smaller scales. And so I'm going to indicate the scale at the bottom here in centimeters. That will be in black. So very early man would have been aware of things roughly on the scale from mountains to insects. And then, of course, as we go further, we got to understand the scale of the planet, for example. I'm also going to summarize on this picture the world view. And, of course, humans started with this geocentric view that the world is. The Earth is the universe, is the world. And then the discovery of microscopes, 10 to the minus 6 centimeters. Astronomical observations, we came to understand, of course, what the sun, the nature of the sun, and the nature of the solar system. At this stage, we've got the heliocentric view, of course, when Copernicus realized that the sun was the center of the universe and not the Earth. So I'm doing this essentially in a historical sequence. And then, of course, Newton discovered the gravitational force. So here I've got the forces in red. And also we discovered the electrical forces and discovered their role in the atoms. And here for the first time, you find there's this link between the atoms and solid objects like the planet. And the reason for that is because it's the same force which keeps the electron in orbit around the proton is what keeps the interstruct with solid matter, intermolecular forces, or hold solid matter together against quantum forces. So that's the first link between the micro and the macro. Meanwhile, in astronomy, we've discovered that the Sun is part of a galaxy, and we come to the view that, in fact, our galaxy is the universe. No one at that stage really believes there's anything beyond the galaxy. There's the picture of our galaxy, but another galaxy like ours. And then, of course, we've got Hubble's discovery of the cosmic expansion, which we've heard all about, and of course, that takes us beyond the galactocentric view. And then, of course, we discover the weak and the strong forces, and we find the weak and the strong forces are actually associated with stars, because it's the same strong force which holds the nuclei together, which is responsible for the conversion of hydrogen into helium and through nuclear burning, and the weak force, which is involved in radioactive decay, is responsible for the regulating those processes. Then we discover the electroweak force, going to smaller and smaller scales as we have more and more particle accelerators. Meanwhile, we've discovered dark matter. From observations of galaxies and their galaxy rotation curves, we found on the astronomical scale there is dark matter. And then what we've discovered is that the WIMPs, that the elementary particles predicted by these sorts of theories, are the favourite candidates for the dark matter. And then we've got the grand unified theory, so we're up to about the 1980s now. And the grand unified theories also relate to this because they tend to be related to inflation and maybe to the fluctuations which are going to give rise to the structure of the scale of galaxies. And then coming up to the 1990s, we're discovering the dark energy on the macroscopic scale. And we're now well into the cosmocentric view, of course, in which most people assume that our universe is exists, at least as the domain of science. But also on the particle physics side, we've come to understand the nature of the vacuum and its connection to the dark energy. So we've got this link between the vacuum and dark energy. And then, of course, at the Big Bang itself, we've got this link between the micro. That's where the head and the tail of the Ouroboros meet. And so we have the multiverse on the right, and we have our universe is just one of many, and then we have the end theory there. So that really completes the picture. And to me, that's like a brief 5-minute summary of the history of physics. But to me, that picture is really inspiring. It sort of testifies the triumph of physics in really coming to understand the unity, if you like, the coherence of the world, the way everything fits together, the connection between the macro world and the micro world, which is sort of epitomized in the Big Bang. And as I said, in some sense, you might want to think of that as the Lemaitre point. So he sort of started that process, and to me that's one of the key points of physics. It links the macro and the micro worlds. Now, however, that's fine, but there's something rather depressing about this picture, because we've got a wonderful description of the physical world, a great intellectual triumph, but of course, what has happened is that we become more and more insignificant. Human beings seem to play, are obviously physically completely insignificant, and it's well, you've read this, you're of no importance, you're the only tiny speck in an enormous universe, and I might as well go back to sleep. Has to wake anybody up in case they're. And of course, this is well summarized by Weinberg: the more the universe seems comprehensible, the more it seems pointless. But now I want to move on to the second great contribution Lemaître, which was to do with the cosmological constant. Because we're going to see the cosmological constant is going to tell us something rather strange about the universe. It's going to introduce this fine-tuning problem. But I want to put this in a more general context, first of all. I'm going to talk about the anthropic principle. And I want to first of all distinguish between various views. I mean, obviously, people started with the anthropocentric view, that the man is the centre of the universe. With Newton, we went on to the mechanistic view, which sort of tends to regard the universe as a giant machine. And our presence in the universe is essentially relevant. Okay? The machine carries on functioning regardless of whether anybody is actually observing it. But then there was this anthropic view, which came around in about the 1960s, at least in terms of modern physics, which was that some features of the universe seem to be required, I've used the word explain there, although philosophers don't like that, by the requirement that life and mind should arise. This is the fine-tuning problem. Now actually, this word anthropic is a terrible word because Brandon Carr coined it because anthropos means man, but whatever this is to do with, it's nothing to do with people. Okay? It's really just a condition that complexity can evolve in the universe, and I prefer to think of it as the complexity principle. The Big Bang has to lead to increasing order and complexity, and brains and mind is just an aspect of that. So I prefer to call it the complexity principle, but anyway, it's the anthropic principle, is how it's called, and of course that's a word some people don't like. Now, let me just give some examples of this. We've heard some of these examples, but the fine-tuning, some of the fine-tunings involve dimensionless numbers which are related to the four forces. Each of the four forces, which I showed on the diagram before, they're described by a dimensionless number, which we call alpha. But the strong force is roughly 10. For the electric force, it's roughly 10 to the minus 2. That's 1 over 137, the fine structure constant. The weak force is 10 to the minus 10. The gravitational force is 10 to the minus 40. So this is all two orders of magnitude. And the question is, will the final theory of everything explain those values? I mean, obviously the hope is that the final theory will explain those values. But the trouble is, they don't seem to. This is the, I think George referred to the paper I did with Martin way back in 1979 in Nature. One of the features of that, you can't read it very well, but maybe that's good because of time. But what we've done in this plot, we take mass against length scale, and we take all the various objects in the universe, like galaxies, stars, planets, human beings, black holes, protons and things, and atoms, and we show that the scale of all those objects is determined in terms of alpha and alpha g, the electric and the gravitational fine structures. You don't need to read them all, and that comes from straight physics. Nothing speculative about that at all. Straight physics. So what it means, let's go back to this Ouroboros. You see, the Ouroboros is quite interesting. It has something like 60 decades of scale, going all the way from the Planck scale, which is something like, well, it's really 10 to the minus 33 to 10 to the 27. But it's like a clock where every minute is a decade of scale. But actually, all of those scales depend upon alpha g. And remember, alpha g is 10 to the minus 40, roughly. So I can write everything in terms of the Planck length, and it goes from alpha 1, alpha g to the minus a half. Men and women, they're alpha g to the minus 3/4. Stars are alpha g to the minus 1, and the universe is alpha g to the minus 3/2. So this is in actual scale in units of the Planck length. So you see, alpha g to the minus 3/2 is 10 to the minus 40 to the minus 3/2, which is 10 to the 6th. But you see, what you notice about this diagram is actually the only reason there's 60 decades around there is because alpha g is 10 to the minus 40. If alpha g had any other value, it would look different. It would squash or it would expand. And furthermore, even this diagram only exists at a certain time. If we look at the universe 10 to the 100 years after the Big Bang, it's going to look completely different. It will be a much bigger universe, and maybe none of these structures exist at all. Maybe we just exist at a special time when all these structures can exist. So the question is, why does alpha G have the value for Lectioperos to arise? Now, there are many coincidences, and I'll go through some of them. Some of them are associated with stars and planets and supernova. We assume in all these arguments, these are still arguments that appeared in the paper with Martin, we assume that life does require planets and stars and supernova and things. And here are just some of the arguments. I know they'll be well known to the astrophysicists here. One of them is to do with the fact that all stars have a mass of alpha G to the minus 3, 2, that's the proton mass. But there are two types of stars. There are stars which which are said to be convective in their envelopes, which means that the heat gets out through convective motion. And these other stars are radiative in the sense that the heat gets out by radiative processes. And the mass at which divides those stars, you can show from straightforward physics. It was an argument Don referred to. It's alpha G to the minus 2 times alpha to the 10th. Well, it's quite a complicated calculation, and Don said we had a factor of 10 or something. But
No, I just dropped it.
oh, you dropped it, fine. But whatever, it roughly looks like that. Now, the remarkable thing is, why does that? The only reason that stars actually exist, this actually is included in the mass range of stars, is because of this remarkable relationship: alpha G is alpha to the 20th. Now, if alpha G was bigger than that, you would only have the stars with convective envelopes. If it was smaller, you would only have stars with radiative envelopes. But actually, you need stars of both kinds. You need stars with radiative envelopes because they're the ones that are going to become supernova. And you need stars with convective envelopes because perhaps they're associated with the stars that we're going to have planets, but for reasons which are a bit dubious and I'm not going to go into. But the point is, that is a coincidence which is observed because the 20th power 10 to the minus 2 is 10 to the minus 40. But it's got no explanation. It's my favourite one. I was asked by, what was my favourite one? That's it. And actually, this goes back to Frank Carr. There's also another coincidence involving the weak and the gravitational forces, which is to do with supernova explosions. There's a supernova explosion. The only reason supernova explode is because when the star collapses, they generate a burst of neutrinos. And those neutrinos throw off the envelope of the star through weak interactions. If the weak interactions are too weak, they would go straight through and have no effect. If they were too strong, they would never get out of the core of the star. So it requires this amazing balance. Alpha G is alpha W to the 4th. That is what's predicted by simple physics. This is observed. The 4th power 10 to the minus 10 is 10 to the minus 40. But it's not explained that it's required for supernova. And in fact, the same coincidence explains why you get an interesting amount of primordial helium in the Big Bang, and also why you have equal amounts of baryonic and dark matter. That's not often appreciated. But the point I want to make is that these relationships are required for life, or at least required for complexity, for planets and stars and supernova, but they're not explained. Now actually there are lots and lots of these coincidences. Here's the famous triple alpha coincidence, which Fred Hoyle realized. The only reason to have life you need carbon. Carbon is built up by the triple alpha. Sorry, the alpha is nothing with the fine structure constant, it's nuclei. And the only reason that happens is because there is a special resonance. You first combine two alphas to form beryllium, and then the beryllium combines with another alpha to form carbon. And that only the beryllium would decay too quickly for that to happen unless there was a finely tuned resonance. And it's been argued that that has to be satisfied to 0.5% in order to get carbon. Now, I have to say, because I know there are some in the audience, that you can be a bit skeptical about this. This is a paper by Helga. And I think the criticism here was about whether or not what it actually had to do with life. But anyway, there's no doubt that that coincidence is required at least to produce carbon. Now, there are many. I'm not going to go through all these. This is a figure from Tegmark about the strong coupling constant versus the electromagnetic coupling constant, and the various disasters that you would have if we didn't live in a very small range. In other words, the alpha strong is also very finely tuned. These are the famous 6 numbers which we've heard of from Martin Rees's book. This is essentially alpha G. This is essentially to do with alpha S. But these are the cosmological quantities, the density of the matter, the density of the cosmological associated with the dark energy, the scale of the fluctuations, the number of spatial dimensions. I don't think I'm going to go through any more of these because you've heard a lot of them about them already. Also, I do want to advertise a forthcoming book by Robin Collins, where he actually has done a really good job in finding many more fine-tunings like this. So hopefully that book will come out soon. But of course, the most famous one, and the one which got so much interest in this, was the cosmological constant. And you've already heard this story. The point is the cosmological constant is 120 orders of magnitude larger than you would expect. John explained this quite nicely this morning. The comparison is between 10 to the 66 centimeters to the -2, which is the Planck length squared, -2, and this is the actual length scale associated with the cosmological constant. Now, what has that got to do with the anthropic principle?
You may need smaller.
I haven't. No,
the line above. You say 120 orders larger than
yes, sorry. Thank you very much, John. Thank you.
Only off by 240 orders of magnitude.
That would be on my 240. Thank you. That could be smaller. Now, Weinberg drew attention because there's no explanation. The most natural value would have been 0. I mean, a lot of people would have assumed it must be 0 for some reason. But of course, we know that's not the case because of the expansion, acceleration. Now, Weinberg pointed out that omega lambda can't be too big. That's the density of the dark matter, the dark energy. It can't be bigger than 0.6 because otherwise galaxies couldn't form. And the probability, in fact, of the observed value is something like 16%, which isn't too bad. I mean, in other words, he was saying that this is the explanation for why it has the value. If it was any much bigger, then you wouldn't have any galaxies. Weinberg tells the story in the book that the editor at first refused to publish this paper because the anthropic word was a taboo word. He said he wasn't going to have anything to do with the anthropic principle in his journal. But then Weinberg pointed out, he was only writing the paper to show that you could disprove the anthropic principle. But then, of course, that was 87, and then, of course, not so long afterwards, they actually measured it, and this was the reason then given. But the key point is that it's all to do with this vacuum energy. Cosmology was giving the evidence for the vacuum from inflation, but particle physics was also giving evidence from the string landscapes and for why you think there's going to be a cosmological constant. And this, of all the fine tunings, this is the one that had the biggest sociological impact, because this is what brought people like Weinberg on board. I don't think it's necessarily the most stunning one, but it's the one which certainly had the biggest effect. I'm not going to go through some of those. Now, but I did mention that, to me, I don't like to think of this in terms of the anthropic principle. I prefer to think of this in terms of the evolution of complexity. So this is what I call a pyramid of complexity, and it shows how, during the process of the Big Bang, you generate increasing orders, a hierarchy of structure. So at about a minute per second, the quarks, you have quarks, and then you produce nucleons at about a few seconds, at 10 to the -4 seconds, and then you start producing atoms at something like 1 million years, and then you start forming galaxies. You get simple molecules, biomolecules. Once you've got life on planets, you've got your cells and your organisms, and then who knows, you get brains and things like that. So this is what happens in the universe, the development of complexity. But the point to make out is, first of all, it only happens, first of all, this happens during the Big Bang. As this pyramid arises in the time since the Big Bang, it evolves. But the other crucial point is that it only arises because there is this balance, this fine-tuning between the various constants. And I've actually, this is a summary in the book, of all the different, if you go through the history of the Big Bang, there are various key events, and they're all associated with these anthropic conditions, some of which I talked about. So, what is undoubtedly true to me is that, well, undoubtedly true, but what is striking to me is that there are these unexplained tunings which are required in order that complexity should arise in the universe. Now, how do physicists react? Well, historically they reacted in different ways. Freeman Dyson, I do not feel like an alien in the universe. The more I examine the universe and I examine the details of its architecture, the more evidence I find that the universe in some sense must have known we were coming. Dyson. However, Heinz Padgett, the influence of the anthropic principle on the contemporary cosmological models has been sterile. It has explained nothing and has even had a negative influence. I would have opted for rejecting anthropic principles, needless clutter in the conceptual repertoire of science. And he represents quite a strong body of opinion. Certainly, when myself and Martin first read our paper on the subject, that was the majority view. But then Brandon Carter, who coined the phrase, take, in my mind, a very healthy view. The anthropic principle is the middle ground between the primitive anthropocentrism of the pre-Copernican age and the equally unjustifiable antithesis that no place or time in the universe can be privileged in any way. Now, what are the explanations? Well, you've heard quite a bit about this, but let me just go briefly. Firstly, of course, maybe God created the universe. Maybe God, this is God with his pen choosing the coupling constants, this is the space of coupling constants, in such a way that the pyramid of complexity can arise. Obviously, most physicists don't like this. I mean, in the Faraday Institute is maybe more popular, but most physicists don't like that. But it's still an interesting issue, whether that is evidence for God. Another explanation was the idea, well, maybe consciousness in some sense creates the universe. And therefore what happens is the universe evolves, it produces brains, which then look back on the Big Bang like we're doing today and bring the universe into existence. This is based on a minority view of consciousness, which arises, as John Wheeler suggested. This is also rather a mystical explanation, perhaps. But then there is, of course, the multiverse explanation, which says that there are many, many universes, we're just in one of them. And the constants vary in all different universes. So just by chance, some of the universes, they can be right for life to arise. So it's like this lottery picture. We all buy lottery tickets. One of us, maybe one in a million, is going to win the prize. Okay, but it's not surprising because somebody's got to win it. So that's the view. Now, by and large, many physicists like this because, of course, it removes the need for God. But I have to say that other cosmologists don't like it either. So a lot of cosmologists think it's just as metaphysical as God. And really, the status of the anthropic principle really all comes down to the question of whether the fundamental theory is going to develop, is going to uniquely determine the parameters of physics, or whether if it's not uniquely determined, you can imagine having all these infinite, not infinite, but a large number of universes, and we are then it's just an anthropic selection spectrum. Here's my favorite picture. Favorite picture of Einstein in his dressing gown. What really interests me is whether God had any choice in the creation of the world. In other words, is the fundamental theory going to actually tell us? Unique as a constant. If you believe these fine-tunings, it can't. Some of the constants have got to be considered. If I can just briefly advertise my book, Universe or Multiverse, George has already referred to it. I think there are only 2 copies left now, and it's cheaper because it's in paperback. Actually, there are only 2 copies to begin now, there are many, many different multiverse scenarios, and there are 4 different categories of the multiverse scenario. Max Tegmark is nice to describe. I think George referred to all these different multiverse scenarios. I won't go through these, we're running out of time. There's sort of level 1, which is just the multiverse region beyond our horizon. There's the sort of different inflationary bubbles is level 2. Level 3 is the quantum many worlds, and level 4 is just the idea that any mathematical structure you can think of exists somewhere. And people have an idea like that, but I'm not really open to 2 and 1. But people have different views. And so, of course, the idea, as we've heard about the Martin slippery slope argument, that the idea is that the observable universe is just a tiny part of physical reality. Now, I want to say something now about, I want to now come on to the issue that George has raised about the nature of science. Yes. The point about this is we've seen that I showed you this Ouroboros. Actually, it's a different version of the Ouroboros. But what I like about the Ouroboros is you can think of it as historically showing how we have expanded our consciousness of the universe to ever larger scales. Okay, so here's primitive man has got that great of scales. 17th century man is sort of so does this and like this, and now we've gone almost all the way around the Ouroboros. So you can think of scientific progress as the expansion to ever smaller and ever larger scales. And the point is, I want to make is that the boundaries on both the micro and the macro sides have always been on the border of physics and metaphysics. I mean, in the sense that you're always addressing questions which are on the border of science. It's nothing new. And the point I want to make is that the nature of science has always changed as it progresses in both the micro and the macro direction. As it addresses new questions. What's particularly interesting now is that in some sense, the micro border and the macro border are met at this point. So you might expect something particularly interesting to happen. And the question is it the end of science, as George would argue, because it's cosmology merging into metacosmology, or is it in some sense the transformation of science? I did have something on the lessons of history, which I'm going to miss because it just takes too long. But the point of this lessons of history was simply that the whole lesson of history is that every time we expand the frontiers, most conservative people will say, this is not proper science. And I'm going to miss this, I'm afraid, because I've run out of time. But I'm sure most of you are aware of that in any case. Every time, I mean, the history of astronomy is the history in which our view of what the universe is gets bigger and bigger and bigger. And at every step, the more conventional astronomers and scientists have just said, that is not the science. But I want to skip that because I'm afraid I just don't have time. So I'm just going to do this very quickly. Of course, never by any means will we be able to study the chemical composition of the stars. The field of positive philosophy lies entirely within the solar system to study the universe being tested in many possible stars. That's just and so this is a reference by Rutherford, 1908. Don't let me hear anyone use the word universe in mind. We've heard all about the problems of even Paul Lemaitre had problems. Einstein, your mass is correct, but your physics is abominable. Eddington, philosophically, the notion of the beginning of the twisted order of nature. We heard a lot about that. Don't be disturbed by an opposition of great scientists. So this was just a lesson in history. And then the Big Bang. Cosmology was then a skeptically regarded discipline not worked in by sensible scientists even in the 40s. Most people did not believe the Big Bang was part of physics. So then the lesson of history is that the universe gets bigger and bigger. Now, but is it proper science? And I will take the view that it's true you can never see these universes, but it may still be science if it's predicted by a respectable theory, like M theory. Because science is full of things you can't actually see. like Martin said, the inside of a black hole or a quark. It doesn't mean you can't see it, it doesn't mean it isn't real. But then the problem is, what happens if these theories are themselves untestable? And a lot of people argue, well, you can't test any theory either, it's mathematics. And that's where the problem comes. You see, the point about science is that it involves, you have an idea, it makes predictions, you make observations, you test or modify the idea. That's how conventional science. But what is crucial to me in science is what is the time scale on which you make these steps. You see, people say M theory is not part of physics because after 20 years we haven't solved the equation and it's not clear we'll ever make contact with observations. Therefore, it's philosophy. But okay, but maybe it will take 100 years. Why should everything be solved in 20 years? But I would have every hope that in 100 years that will solve the problem and make contact with physics. So are you going to say that it's not science because we looked at 100 years? There are all sorts of tricky issues here, which I'm trying to get saying why I in some sense disagree with George. So I agree with George that you need falsifiability, but the question is on what's science. And finally, I'm sorry I've gone on through my, never mind this. I think one of the interesting issues is when we talk about the nature of science and how it's going to change, I actually think the question of mind and consciousness is really crucial. You see, people sometimes ask, well, what are the anthropic fine-tuning really about? I said it's complexity, but because the original anthropic arguments were that it was the presence of observers, something to do with consciousness. So now we come back to the question of, well, in fact, is consciousness the relevant selection criteria in these anthropic fine-tunings? And if so, what level of consciousness? Does it have to be a professor of mathematics or a theologian, or can it be a dog? And those are the sort of questions. I actually think that there is something important about consciousness and mentality of the universe. This is the famous pyramid of complexity. I like to ultimately what with consciousness, mind, and it's spirit, which is what's of interest to theologians, is just for me just part of this process. So to me, although these are taboo words among physicists, to me it is just a natural part, a natural combination of this pyramid of complexity. And physical, biological, and if you like, mental levels. To me, it's all part of the same process. So I think that consciousness is going to be really crucial. So I'm looking at about consciousness. And I think there are various arguments that mind really is significant in the universe. Many people have said this before. I'm now over on time, so I'm going to actually leave it that point. So the point is the significance of mind from comprehensibility of the universe, the beauty of the universe, and the fact that even our physical paradigms are essentially models, mental models. So I think mind is significant, and I wanted to end on that sort of note. But let me just, of course, is there room for God? That's a different, deeper question, which I'm not now going to go into. Let me just, I had a meeting on, Rodney, I better skip this, I think, because
I think we're
going to go straight to the final. I'm going to skip God. The point was I organised a meeting in Cambridge only a year or two ago called God or Multiverse, and then Rodney and John Polkinghorne were there. I don't want to go into that, I just want to show I'm interested in that issue.
Really quick.
Sorry?
Show your slides really quick.
Well, I mean, I'm happy to get into the discussion later if somebody wants, but I want to sort of end up. The point I want to make, though, just to finish, some physicists I've mentioned really favour the multiverse because it avoids the creator. But many people have made the argument that both ideas are equally metaphysical. Paul David, for example. And it's clear that this dichotomy is too simplistic. As far as I'm concerned, if God could create the universe, he could create a multiverse. So whether there is a multiverse is, to my mind, completely indifferent as to whether or not there's a God. I think what is interesting is that in there really is only one universe, then you really are going to have a problem explaining those fine-tunings. This is what Neil Maxson made the remark, the multiverse is the last resort of the best behaviors. And so I'm ending. You can't really talk about God in physicists, but it's an interesting phenomenon that as you go through history, you've got your anthropic and your anthropic word that used to be taboo, and that was, I'll talk about that. The word consciousness, you didn't used to be able to talk about, but even that's becoming now respectable. I think it will be quite a long time before talking about thought will be respectable among physicists, but it's certainly nice to be able to talk about that topic. Thank you.